All right, I think it's, yeah. Yeah, it's recording. Okay, good deal. All right, guys, so we're going to start waves. So here we go. All right, this is what we did, what we already said in the bell ringer. A wave is a rhythmic disturbance. We said it's characterized by disturbance. So if you throw a rock into a pond, it's going to disturb the pond, and it's a disturbance. So it's a rhythmic disturbance that transfers energy through matter or space. And then it says carries energy without carrying matter from place to place. That's key. This is a key thing. And it's one of the things that makes waves really unique is they can carry energy without carrying matter from place to place. Because think about this for just a second. And there's many different types of waves. So think about like the sun. Okay, we got this big ball of fire in the sky. It's a giant nuclear reactor that's constantly, there's explosions going on all the time, right, that keeps it going. How does the energy, if energy had to transfer matter, right, or it couldn't go through empty space, there'd be no way for the energy from the sun to get to Earth, right? And that's like how life is, most life on Earth is dependent upon photosynthesis, which energy comes from the sun and makes the plants grow, ultimately, right? So energy has to be able to transfer through a vacuum. So let's think of this for a second. What if we were to do this? Now, we may have said this before. What if somebody were to take a vacuum and suck out all the air in the room? Would you be able to hear me talk right now? No, right? But if I had a heater, if I had an infrared heater up here at the front, would you be able to feel the heat? Yes. Why? The answer is yes. You would be able, you're correct in your answer. So you wouldn't be able to hear me talk because sound waves require a medium to travel through. But a heater, which displays infrared heat, can travel through because heat, you ever feel the heat of the sun? Yeah, of course, right? It's infrared, right? So that heat can be transferred through space without a medium. So you can actually feel the heat from a heater without air, okay? Now, would you be able to feel, now you may say, well, you could have a heater that blows the air, right? And you feel the warm air molecules bump into your body, but that's different, right, than feeling infrared heat. Animals use infrared, right? Like a snake or a reptile. Its tongue, right, it basically can see in infrared, right? So if you have a mammal, like a little rodent or something, and a snake's hunting, it doesn't see like we see necessarily, right? I don't know snake vision exactly, but I know a snake, if they use their tongue, what they're doing is they're tasting the air, right? And they're seeing through infrared. So they can look out there and they see a landscape that's all kind of, in some sense, like we look through infrared goggles, it's like cold, right? But then all of a sudden they see a warm area. Well, you know what that warm area is? It's probably a rodent, right? And they'll strike the warm area. So they don't actually have to see the rodent. They can see its warmth. They can strike the warm area and then go find the rodent later, once it dies from the venom. Anyway, that's all wave stuff, okay? And there's so much more to it than that. All right, a lot here, guys. So go ahead and write down what electromagnetic waves are. Go ahead and write down what mechanical waves are. And then in just a minute, we'll discuss this a little bit more. And a cool picture here to discuss, right? This dude or maybe it's, I don't know, person in outer space with their astronaut with their spacesuit on. This is a cool thought. Say that astronaut had a cell phone, right? And he was trying to talk on a cell phone. Like say he had a cell phone in his hand. Okay, and he pulled it up to his helmet, and he started talking. Would the person be able to hear him on the cell phone, on the other end of the cell phone? No. Why not? So first off, does just the distance matter? Think about. Okay, first off, let's answer this question. When he hit send on the cell phone, he's in outer space. Would it be able to call somebody else? let's say it's a satellite phone. It may not actually work from Earth, but say it's a satellite phone. Would he be able to call? Yes, he would, because we know that the signal that comes out of that cell phone, it's like a microwave signal, same thing as like we use to cook food with. It's just less powerful. It would be able to communicate with the satellite. The satellite would be able to communicate with the person's phone, and they'd be able to call them. But the question is would he be able to talk? And we already know the answer to this. Would he be able to talk? No, right? Because his voice, it wouldn't resonate. He would hear it in there, but it couldn't get outside of his helmet, because even there's no air molecules to vibrate, right? Now ask this question. I think, though, if you were to literally take the speaker of the cell phone, just thinking out loud here, and put it up against his helmet like this, they might be able to make out something. Because if you think about it, there's air obviously in his suit, and if his voice vibrates the air molecules and it touches the helmet, and if it vibrated the helmet correctly, that speaker might be able to pick it up, right? Because it could feel the vibrations vibrate the speaker, which basically is how a speaker works, right? Vibrations picked up by a magnet that are transferred to a signal, and they might be able to hear. So it's just some really cool thoughts. It's like things that you start putting these puzzle pieces together, and you can kind of think, oh shoot, it's kind of neat. All right, so examples of electromagnetic waves. So let's test question. This would be a test question. This would be a quiz question. How are electromagnetic waves different than mechanical waves? Answer to that question would be something like electromagnetic waves can move through a vacuum or space, right? Because they can move through a vacuum. Example, light. So electromagnetic waves are light waves. Y'all know the electromagnetic spectrum? Seen that before? Starts off, it goes like radio, then microwave, then infrared, visible light, then ultraviolet, X-ray, and then gamma rays. I know what I'm talking about? Okay. That's the electromagnetic spectrum, right? And we basically experience all those different wavelengths. Well, maybe not X-ray and gamma ray for the most part. If you did, it may not be good, right? What do you have to do when you go get an X-ray? Yeah, and what's the technician do? They go in a different room. Why do they do that? Yeah, X-rays are dangerous. And you may say, well, why do I get an X-ray then? Well, we're just saying that you don't get exposed to enough of it, right? If you took X-rays every day, you would probably get cancer. Not probably, you would get cancer. Something bad would happen to you, right? Because X-rays, so when you go up, and we'll get into this more, I'm kind of getting ahead, but when you go up in energy or up in frequency through the electromagnetic spectrum, the wave becomes more like a particle, which is this, and this stuff gets really weird. Honestly, it's hard for me to understand and grasp. And so I'll try to, it'll probably be hard for you because if I'm telling you about it. But anyway, it gets more energetic, and it can start to damage stuff, right? What do we know from ultraviolet light? What do you have to do? Ultraviolet light, why do you have to be careful of that? We talked about it just a little while ago. Yeah, sun. But we also know that ultraviolet light actually is really good for you because ultraviolet light promotes the production of vitamin D. Right? So there's some ultraviolet light is actually really beneficial. Go get in the sun. Right? But too much can literally chemically burn your skin, destroy your DNA, and ultimately, if it happens enough, it could cause cancer. Now, your body can repair its DNA through a lot of different mechanisms, but too much damage, and it cannot repair it, and you get a broken cell, and you ultimately get cancer. So the more energetic the wave, the more chance it is to destroy your DNA. So that's why in X-rays, you don't just want to get X-rays all the time. You want to limit that stuff. And then on Earth, I would think you're almost never exposed to stuff like gamma rays, unless you're around a nuclear explosion, or the remnants. You won't be around if you're around nuclear explosion. But if you're around like if you have a piece of uranium, okay, that's radioactive, it emits gamma rays, it emits alpha particles, beta particles, all these different types of radiation. They get emitted. So anyway, that's a lot for electromagnetic waves, but we're going to get way more into that as we go through. So that's electromagnetic wave. All electromagnetic waves propagate or move. How fast do they move? Anybody know? That's right. They move at the speed of light. You know how fast that is? Very fast. It's 3 times 10 to the 8th meters per second. So if you draw that number on the board, it's really fast. It can go, it takes about, but if you think about this for a second, as fast as that is, do you know, as fast, that's really fast, guys. That's really fast. So, but as fast as that is, it would, this is just a cool fact, it would still take, I think, about 4.5 years going that fast to get to the next closest star in our solar system. So if you were to get on a ship and accelerate towards the speed of light and then travel at the speed of light, it'd still take you over 4 years to get to, I think it's called Alpha Centauri, get to the next closest star and planets associated with that. That's nuts, man. So even so, a lot of people like space travel and going through the galaxy. We need something really even faster than the speed of light. We need like wormholes, or we need some way to warp space itself and like move space or figure out how to go faster than the speed of light. I don't know, a lot of crazy theoretical stuff right there, but so space is huge. Right. Okay. All right. So light waves, all electromagnetic waves move at the speed of light. Okay? All right, mechanical waves, they do not move at the speed of light. They move much, much slower than the speed of light. So a mechanical wave example of that is sound waves, water waves, seismic waves. Seismic waves, like that move through the earth after an earthquake. Those would be a mechanical wave. The key, like a test question, maybe something like, what makes, well, there's a lot of reasons why, but what makes mechanical waves unique? They have to, what is it? Well, yes, they're slower, that's a good point, but they have to travel through a medium. They have to have something to travel through. To propagate, yeah, they have to travel through matter. Exactly right. They have to be able to, for them to, but they don't move matter, but for the energy to go from point A to point B, they have to have matter to travel through. Okay? All right, cool. And if you have a question, please ask or comment. All this stuff makes you got to speak to think. So feel free. Put on a jacket. I'm sorry. The heat is where it is right now. So here we go, guys. Take your time and write this down, guys. Take a minute, and it's a lot to write here. And I've got slinkies. We'll use slinkies to, yeah, not today, but we'll get some slinkies and do some cool wave demonstrations with slinkies. Let me see if I can change the air, Cammy. All right, I'm leaving where it is. Okay. Okay. All right, so as you're writing, I know it's a lot here, but always abbreviate things. Take notes as you see fit to get the information down. All right, transverse. Transverse waves, it says matter in the medium moves back and forth at right angles to the direction that the wave is traveling. All right, so that means if a wave is traveling that way, the direction is going that way, matter in the medium moves back and forth at right angles. Anybody play guitar? Okay, so when you play the guitar and you pluck the string, if you look at it, it kind of looks like this, right? Right, so the vibration of the string makes a transverse wave. Electromagnetic waves are transverse waves. Ripples in the surface of a pond are transverse waves. These are all waves that the matter moves up and down relative to the direction that the wave is traveling. So we'd categorize those as transverse. Okay. Now this is really cool. These longitudinal waves. The best example of a longitudinal wave to me is sound. Right. Sound waves are compressional waves. And I want to show you, there's a YouTube video we'll watch in just a second, This is an example of a Rubens tube. We've seen the Rubens tube before, haven't we? Yeah, where it play the song and the fire. Yeah, okay, so there's another one in just a second where he does a little bit more description of it, but it's super cool. And it's a way to visualize a sound wave. All right, so when I'm speaking to you, if I were to make a noise like, right, that noise, yeah, terrible noise. That noise is propagating through space, and what it's doing to the air molecules is it's compressing them, and then, so at places as it travels through space, there's compressions and there's places called refractions, where the air molecules are compressed, and there's places where they're spread out. And that's how it propagates through space. And so to visualize that, you can use something like a Rubens tube, and you can actually see the wave, which is super cool. You can actually see the wavelength. You can measure it. You could play the sound and then take a ruler and measure the wavelength of the sound wave, which is really cool. And as you expect, what do you think? Higher pitch sounds, do they have a shorter or longer wavelength?
Shorter.
Okay, so think about it. Just think about it. So if I make the sound, which one has a longer wavelength?
Higher.
Let's draw it on the board. Okay, I'm just going to draw it. That's this because I think this will make it better. Better. Okay. All right, let's do it right here. So here's the first sound. Here's the second sound. Okay? This is, which one is which? This is the high pitch. Right? And that's the low pitch. Exactly. That's right. That's right. So this is, and this is, right? So typically, the way sound propagates through, the higher the frequency, or the higher the way it sounds to you, the pitch, right, the closer this wavelength is going to be. And you can actually see this in the video when they play different sounds. You can see the wavelength change. And the lower sound is going to have a longer wavelength as you go longer and longer and longer. Okay? But the way this really works is if you were to draw this another way, right, you can visualize it like this, but really it's like this. If I were to draw a tube, the way this really works, we draw two tubes, all right, say there's air molecules in this tube, okay, like oxygen, nitrogen, all kind of stuff, right here. So you could draw it like this. Where there's a trough, the bottom, this is a trough. We'll look at this in a sec. Trough and a crest. Okay, and we'll label them in a second. Where there's a crest, the air molecules are compressed. Where there's a trough, the air molecules are spread out. And it's the same thing. Okay, can you kind of see what I did there? Does that make sense? So where there's peaks, the air molecules are compressed. There's compression there. And where they're spread out, there's refraction there. So the air molecules are more spread out. And obviously here it's going to be compression, nothing much, compression, nothing much, compression. It will look like that. And when you do this with a Rubens tube, you can see it, right? Because there's going to be a big flame right there, and then little smaller flames and tiny flame, right? Tiny, bigger, big flame, right? You get what I'm saying? And it'll look like, and then you could literally measure the wavelength. You can measure the distance from here to here, and say, hey, that's 1 meter. I don't know what it would be. Just say it. That's probably too big. But anyway, whatever it is, 1 meter, and then that frequency has a wavelength of 1 meter, literally. It's pretty cool. Okay. So anyway, I get excited about that stuff. I'd really like to get with Coach Harris and make one of these. That would be fantastic. All right, let's keep going, guys. Okay. All right, so this is really simple. Just label this really quickly. This is important But just label, I think this is stuff that you've had from a long time ago in school. But just label this because everybody needs to know, hey, the top's called a crest. The bottom's called a trough. The middle is the normal or resting point of a wave. Okay? And we'll label more stuff with that. Okay, so simple enough. Any questions about that? What type of wave is that? Not specifically, just generally. There's two types of waves in the last slide. Transverse. Yeah, exactly. It's transverse. When you show you compressional, you see this. Okay, so that's a compressional wave. That's what I was drawing on the board just a second ago in my terrible drawing. So in general, this would be called a transverse wave. This would be called a compressional wave. Okay, so go ahead and label this. This is what I was talking about. So you can show this with a slinky, and we'll show it with a slinky as well. Compression are the parts where in the wave where they're pushed together. Okay, like we said right here. And a rarefaction is where the particles are spread apart. So where would the flame, if this was a Rubens tube, if this was the inside of a Rubens tube, where would the flame be highest? At the compression or the rarefaction? The compression, that's right. Exactly right, because that's where the pressure is the highest, right? Because think about it, pressure, when you say, hey, that's high pressure, all that means is the molecules are tightly packed, right? When you increase the pressure, if I increase the pressure in something, I'm pushing more air into it, right? If I increase the pressure in this balloon, I just keep pushing more air into the balloon. So there's a lot of pressure right here, thus the flame will be really high. Right? So that's all that is, and the flame will be low here. It'll be lowest in the middle of the compression and highest in the middle of it will be lowest in the middle of the rarefaction and highest in the middle of the compression. Okay, so this will probably be, our last one. Okay, so amplitude. Amplitude is the amount of energy carried by a wave, guys. So just, again, label the wave, and measure what the amplitude is. And this is one that's confused a little bit, so we're going to talk about this one some. So, how do you increase the amplitude of a wave? What do you have to do? Think about your radio. How do you increase the amplitude of the wave coming out of a speaker? What is it? Say it again. I think you said it. That's it. It's the amount of volume. Very good. Y'all get that? So let me ask you this. Does increasing the amplitude change the wavelength? Does it change the wavelength when you increase the amplitude? No, it does not. Okay? Does it increase the frequency? Did you change your channel on the radio? No, right? Didn't change. Remember, when you turn your radio to 93.3 or whatever it is, whatever you turn your radio to, that's changing the frequency, right? If I change it to 93.7, I just change the frequency to 93.7 hertz. Okay? When I turn the volume up, I don't change the frequency. That's changing the amplitude, right? So you're giving it more power, in other words, right? So you change the amplitude, doesn't change the wavelength, it doesn't change the speed, it doesn't change the frequency. Amplitude just changes the energy the wave has. Okay, let's change that. The power the wave has. It makes this bigger, right? The distance between the resting position of the wave and a crest or a trough, that's what you increase when you turn the volume up. an amplitude. Okay? All right, cool, guys. Any questions? We'll get to actual wavelength and frequency period later, yeah. Questions? All right. Okay, cool. So, give me an example of electromagnetic wave. Quickly. Yes, microwave. Beautiful. Yes. What's another one? What? No, sound is not electromagnetic. Think. Sound is a mechanical wave. Good. What? Gamma rays. Good. What's another one? Ultraviolet. Good. Yes, those are electromagnetic waves. Okay. So then I would say, give me an example of a mechanical wave.
Can lightning be
No. But good thinking, girl. Answer it out. Good. What? No. Okay, Cammie, electromagnetic waves travel through a vacuum. Okay? Electromagnetic waves travel through a vacuum. What's a mechanical wave? You said one a second ago. Sound. What else? Light's electromagnetic. Yep. No, X-ray's electromagnetic. Drop a rock into a water, right? Water waves. Yes, that's a mechanical wave. Okay, so you see, sometimes this stuff is always a little bit more difficult than you think. Like you think you got it and you don't. Okay, so electromagnetic waves, radio, infrared, or go through the waves: radio, microwave, infrared, visible light, ultraviolet, X-ray, gamma. Okay, that's the electromagnetic spectrum. Then those are all electromagnetic waves. Mechanical waves, sound, water waves, seismic waves. What's the big difference? Mechanical waves have to travel through a medium. Good. Electromagnetic waves do not. Okay, good. All right. Excellent, guys.